Good morning, everybody. It is Monday morning East Coast time, Monday afternoon in Cologne. So I hope you all had a good weekend. Today we're going to have two lectures. The first one is going to be about price discrimination and also the limits about price discrimination. And in the first lecture, we will see within the context of a classic problem in optimal pricing how important the role of information is. And then in the second lecture, that will be about Bayesian persuasion and information design, we will try to trace out in a little bit more detail how impactful information can be to align and realign the incentives of sender and receiver, or principal and agents. Okay, so that will be the program of today. I mentioned earlier in my lectures on Friday that the smart students and the smart professors always ask questions in class. And in fact, the more question, the better. So I think active learning is really very important. And so I would encourage you to A, switch on your video, and then B, do ask questions, which are really welcome and which will also help me understand better your background and what might be difficult and what might be easy issues for you. All right. So having said that, the paper today, or the talk and the lecture today, is actually based on a paper that has the title "The Limits of Price Discrimination," and that came out in the American Economic Review 5 years ago, pretty much exactly 2015, and since then has led to a lot of interesting follow-up work. So I hope you'll find the material interesting. But since it's a classic economic issue, it's one that is going to help us understand and also rephrase a little bit what we saw in the lectures on Friday. Okay, so price discrimination is really a classic issue in the analysis of monopoly, and it basically asks to what extent a seller can use discriminatory pricing, and by that I mean simply pricing that can differ across segments of the markets, how it can affect consumer and producer surplus. In a way, price discrimination is the simplest and the easiest optimal monopoly setting, because we're basically thinking of setting the optimal price vis-a-vis a consumer who has a unit demand. So in some sense, a lot of the things that you already have seen with Peter on optimal auctions is now going to be recast in an even simpler setting of not just many bidders, but in fact just a single bidder. Okay, but it will be helpful to have this as a starting point to pursue a few other things. Okay. The language that we're going to use comes all the way back from Pigou, who said that a monopolist engages in third-degree price discrimination if he uses any additional information beyond what he knows about the aggregate distribution of buyers, such as the consumer characteristics, to offer different prices to different segments in the market. Okay. What is key here is that there's a relationship between the segmentation that the seller can attain in a market and the information that allows him to pursue that segmentation. Okay. So if he has additional information about the valuation of the consumers, then he can match, or rather tailor the prices that he's offering to the consumer characteristics. And the big question that we're going to pursue today is, as we vary the information that the seller has about the buyers, what are the possible pairs in terms of consumer surplus and producer surplus that can be obtained for some kind of information and for some kind of segmentation that we will get in the market. In other words, what we want to know is what are the possible outcomes that come from third-degree price discrimination. Okay. The question of price discrimination was first posed by Pigou in the 1920s. So you might say this should be a matter that is settled for economics by now. But in fact, it's a very modern issue. Why? Because until maybe 10, 15 years ago, we thought of market segmentations being issues that are rather exogenous. That is, one can think about the location, whether it's in an urban environment or in a rural environment. One could think about the time, whether one offers movies at 3 o'clock in the afternoon, 5 o'clock, or 7 o'clock in the afternoon. Or one could think about age, pension years against people in the workforce, students as opposed on the university, students in high school as opposed to people in the workforce. And so one could think about these segmentations as largely arising from fixed description of the characteristics. But increasingly, with data intermediaries collecting and distributing a lot of this information, that's of course happening in marketing all the time, but now think about digital platforms such as Facebook and Google, having a lot of information about the interest and the characteristics of consumers. We can think about these consumer segmentations as increasingly the endogenous variable, choice variables that the platform thinks about supporting. And so therefore, if more information becomes available, the segmentation becomes largely endogenous. Okay. How the segmentation will be chosen will depend a little bit on the market structure. So if the data is collected directly by the seller, then of course he will try to get as much information, much surplus from the consumers. If, on the other hand, the data is collected by the intermediary, then the intermediary could have interests that are much more aligned with the consumer because, for example, the intermediary would want to get as many consumers on its platform as possible. And so segmentation has also important implication for how we think about privacy regulation. That's a big issue in the European Union at the moment, about data collection, data sharing. So really the topic that we're covering today has implications that go far beyond the simple economics that we're discussing. Okay. But let me give you a first pass at the problem. And let me do this almost entirely geometrical with really very little math involved. And after I have given you the basic idea and the direction that we're going with just a few drawings, then we're going to give a model, and with the model will then come the corresponding analytics and proof ideas that will underlie the result. Okay, good. So as I said, questions are more than welcome, and your presence on the platform, as it were in Zoom, is also more than welcome, so that I get a sense where you are. Okay, so think about fixing a demand curve. That's simply an expression as of the heterogeneity of consumers who all have a single unit demand for the object, but there can be many of them, and there can be heterogeneity in terms of how much they're maximally willing to pay for the object. So this will give me a demand curve. Okay. If the monopolist now is selling the good, we can ask, what is the producer surplus? That is the monopoly profits. And what is the consumer surplus? That's simply the area under the demand curve. Okay. And if the seller cannot discriminate between consumers, then he must simply charge a uniform monopoly price across all of the consumers. Okay. What does this give us? I'm going to see whether I can improve the view here. I want a single page. That is much better. Thank you. Okay, so I said I'm going to first give you the result essentially in a few pictures, in a few illustrations, and a few graphs, and then we're going to do the analytics behind it. Okay, so if the seller were going to charge just a single price, then there would be some consumers who would find that their value exceeds that price. They would buy the object. They would realize a surplus that is between their value, B, and the price they're being charged. If we sum this up over all consumers, that gives us a consumer surplus. That's a U star, which is this plotted on the x-axis. And on the other hand, it will also give us a revenue. That's the producer surplus, and that's pi star. Okay, so if you're pricing against the aggregate market, the seller has no ability to discriminate among the consumers. The best thing he can do is just charge a single price and simply hope that a large number of buyers will buy at that price. Okay, the market outcome is going to be simply represented by a pair of consumer surplus U star and producer surplus pi star. Okay. Now, that is just one outcome that is supported if we have zero information. On the other hand, we could ask, what if the producer could in fact observe each consumer's valuation, each individual consumer's valuation perfectly? Pigou in the 1920s called this first-degree price discrimination, or often it is referred to as perfect price discrimination. Well, in that, in some sense, opposite case, where now the producer has complete information about the willingness to pay of the consumers, the consumer can get all of the surplus, and the producer can get all of the surplus. In fact, the consumer gets zero surplus because he's being charged a price at which he's just indifferent between buying and not. Okay, but the outcome is going to be efficient because we're going to sell the object if and only if the value is positive, and we will find a price that supports that realization of the surplus. Okay, so even though it's an outcome that in terms of net utility is clearly not favorable to the consumer, from a social point of view, we're just thinking about maximizing producer and consumer surplus. This outcome is actually fully efficient because we attain the efficient outcome. Okay. So we are therefore getting a second red dot, okay, that is now sitting on the y-axis and indicated by y star here, okay. Yes, and that lands on the 45-degree line, which marks the sum of the efficient producer and consumer surplus. Okay. Clearly an outcome that is much preferred by the producer because it gives us a higher surplus, and one that leaves the consumer with net surplus. Okay. The question now is, are other outcomes between this outcome here and this outcome down there possible? And what exactly is possible if we let the information that the seller has vary between zero information, which gave us the first point, and complete information, which gives us the second point? Okay. That's a question that we're going to try to pursue. That is, let's suppose that the producer gets some information, it might be just an imperfect signal of each consumer's valuation, and then could charge possibly different prices based on that signal. Okay. This is as if we were going to ask, what happens if we're splitting the markets into different segments? Students, non-students, old age pensioners, and so on. Okay. I mentioned already that Pigou called this third-degree price discrimination, and he asked what can happen. And in fact, a large literature starting with Pigou asks what can happen to consumer and producer surplus. So we are going to therefore contribute to that literature. And our main question is today, what could happen to consumer and producer surplus, thus the total surplus to all possible ways of segmenting the market. Okay. And our main result that I'm going to try to convey today is that we can get a complete characterization of all possible pairs that can arise due to some segmentation and due to some information that we could give to the firm, to the producer. Okay. So that's the main result. And now let me try to give you a visual representation of that main result before I'm presenting you the model. Okay. And I'm going to give you the result by means of 3 simple bounds on the payoffs. That is the pair of payoffs of producer and consumer. Okay. The first bound, the first of these 3 bounds, is easy. The consumer surplus has to be at least 0, because the consumer can always refuse to accept the price, and that leaves him with his outside option, which is simply normalized to 0. So it will always have to be the case that the consumer is given a consumer surplus that is non-negative. Okay. And so the 3 arrows here, right, that are pointing outside are basically giving me the first bound. It must be the case that whatever we get from segmentation, whatever we get from price discrimination, leaves the consumer with a non-negative surplus. And as we saw before, when we looked at this particular point here, it will often leave him with quite a bit of consumer surplus. The second pair of bound is what I may refer to as non-negative value of information. If the producer gets any information about how his consumers look like, that is, whether they're students, whether they're employees, whether they're retirees, he can use that information in his pricing, but he could always disregard it. Okay. And if he were to disregard it and just pursue a uniform price, then he would get a uniform monopoly profit. So this tells us that with any additional information, he must be able in expectation to do as well as he could if he were to simply disregard all of that information and pursue his uniform monopoly pricing profit. Okay. Right. And the third bound is then, of course, given by the social surplus. The best that consumer and producer can do together can never exceed the total gains from trade. We made the implicit assumption that the cost of production is equal to 0. So the total gains from trade is simply the value, the willingness to pay of the consumer for the product. Translating this into our diagram, where I recall that the x-axis plots the consumer surplus and the y-axis plots the producer surplus, we get a triangle. We may think about or refer to this as the surplus triangle. That indicates to us, for some reason my pen is not working as brilliantly as it did last week, okay. And that surplus triangle is basically a set of all feasible pairs of consumer and producer surplus that satisfies the 3 bounds that I just gave you. Okay. Okay. And you may remember that we basically have a point that includes the perfect price discrimination. We have the point that includes the uniform profit. And of course, many other possibilities seem feasible. Okay. So, for example, I might think that convex combinations, that is, having sometimes perfect information and having sometimes complete information, having sometimes no information, would give us a convex set between these 2 points, would give us sort of a lens in which we could realize pairs of surplus. But in fact, the main result that I'm going to try to establish for you today is that the segmentation that can be supported through some information policy are so large and so powerful that in fact any possible pair in that surplus triangle can be realized as some form of price discrimination. Okay. Maybe just stare at this triangle for a second, okay, and think about its implication. Okay, think about its policy implications when we wonder whether firms should be able to access additional information about segments of the consumers in order to allow for more tailored, for more personalized pricing possibly. Okay. The first implication that we have is that it looks like as if this definitely is going to increase the producer surplus, the profit of the firm. Okay, so there is no question that this may be valuable for the firm, or in fact will be valuable for the firm. The second question that we could ask is, will it be valuable for the consumer? Okay, and the third question that we could ask, will it be valuable for society as a whole, that is for the sum of the producer and the consumer surplus? Okay, and so this gives us this direction for the consumer, and that gives us another direction that basically comes from a 45-degree line that goes through here, which is the consumer and the consumer and the producer surplus. Oops. Well, there's really an issue with my pen today. Okay, that these are the three directions that we can attain. Okay, and what we find is that since we can, starting at this point where we have no segmentation, we can always, let me just use a different color and see whether that will help. Well, that doesn't give me anything. Okay, so I'll stop it for a bit and hope that it will charge or something else will happen. Good. What we see from this picture is that we're starting out at the point of no information, that there will always be directions in which we can increase not only producer surplus, but also social welfare and also the consumer surplus. So a priori, we cannot say that more market segmentation will lead to depression of social surplus or consumer surplus, though the possibility clearly exists. Okay. Okay, and so a verbal statement of the graph that I just gave you is that for any demand curve, any pair consistent with the three bounds can arise through some segmentation and some information structure. In particular, there exists a consumer surplus maximizing segmentation, where more information does not help the producer in the sense that he earns exactly his uniform monopoly profit, where the allocation is sufficient and all of the additional information simply leads to an efficient allocation that the consumer can gain from. And in fact, the additional consumer surplus that is gained is precisely the difference between the efficient surplus and the uniform monopoly profit. So that's a very strong result. But then there's also social surplus minimizing segmentation, where the producer doesn't earn any more profit, that is the uniform monopoly profit. The consumer actually gets zero surplus, but the consequent allocation is very inefficient. Okay. And so these two additional allocation, the consumer surplus maximizing allocation, is identified by the black dot on the right, okay, where we are at the boundary of the social surplus, but we also have pushed the producer surplus as far out as possible, okay? And the social surplus minimizing allocation is identified by the black dot to the left that's sitting right on the y-axis, in which we have not achieved any gains in producer surplus, that we are exactly the same horizontal level, but we have reduced the consumer surplus all the way down to zero. Okay. We have also moved very far away from the 45-degree line. Okay. In fact, we have moved the furthest away that we can move. And so we clearly are now obtaining a very inefficient allocation, one that benefits neither the producer nor the consumer and clearly damages the consumer quite a bit. So the effects of segmentation can always be positive, but sadly can also be negative, and therefore we may want to think later on a little bit about what are the implications, or what are good information structures and what are bad information structures for welfare maximization. Okay, excellent. Good. Last time I'm going to mention this in the lecture today. Please feel free to ask questions, in class and on Zoom. And if there's anything that you find difficult to assess or difficult to understand, or that would be helpful for further clarification. Okay. But if not, then I'm going now to, after this geometric representation of the result, I'm now going to give you a formal model in which we can pose these questions, and then give you a formal statement of the result and give you some insights into the nature of the arguments that support that. Excellent. Okay, so here's the model. We think about a continuum of consumers. So simply a probability distribution of consumers. These consumers can have a valuation, and for the purposes of the talk today, we're going to simply assume that there's only a finite set of possible valuations starting at 0 and going all the way up to the K, capital K, which is the highest possible valuation. Okay. There's going to be a constant marginal cost of production for the seller. So, and we're going to normalize this to 0. In other words, V is the net value, the social net value of producing the good. Okay. So here is where we want to go a little bit slow and explain the setup of the model a little bit, but it should be pretty transparent. Okay. So we basically want to think about the market as a probability vector that specifies, which is entry of the vector, the proportion of consumer who have valuation VK. Okay. So X is the market that characterizes the market. It is a vector that gives us the proportion of consumers with any specific valuations. Okay. So here it is where it's helpful to think about just a finite set of valuation, because we basically have a finite dimensional representation of what the market is. Okay. And then the set of possible markets is simply what we call a k-dimensional simplex, because it is simply any possible probabilities distribution over these k valuations from 1 to k, capital K. The entries xk have to be non-negative, and they have to sum up to 1. Okay, because of that constraint that they have to sum up to 1, we have a k-dimensional simplex. That is, we have k minus 1 free variables. The k's variable is then going to be determined by the restriction that we want to think about, a probability distribution. Okay. Okay. Now, the market, from the point of view of the producer, is just a distribution over this valuation. So it's simply a vector X. Okay. And we say that the price VI is optimal for a given market X if and only if charging that price VI gives us a higher revenue than charging any other valuation VK. Okay. You may have seen this revenue calculation done with a continuum of valuation, therefore a cumulative probability distribution, a density function. I'll come back in a second to do the translation for you. But for the moment, let's try to understand what this formula is saying. It is simply saying that if we're charging a price VI, okay, then who is willing to buy? This is very odd. Okay, my pen seems to have given up. If we are willing to buy at the value VI, then who is willing to buy? So if you're selling the object at price VI, who's willing to buy the object? Well, all the valuations who exceeding the valuation VI. So we're summing up over all of the entries xj that are larger than I. Okay, we could charge another price. Since the valuation are on this grid, it doesn't make sense to charge a price that is different from any one of the valuation which is on this grid. So take any other valuation which is on that grid. That would give us a price VK. We would ask how many people would be willing to buy at that price VK. Well, it's all those people who have a valuation that is equal or exceeds VK. And so we're summing up again over the probability over all those people who have a valuation that is weakly larger than K. Okay. And with this, we can then say, what are the set of markets where that is, what are the probability distributions where charging the price VI is optimal, that is, where this gives us a higher revenue than any other price that we could charge. Okay. Good. And if we basically form these sets, one for every possible valuation, so that's the X, capital XI, we basically split the probability simplex into many convex polytopes, each one of them giving us a set of probability distribution where charging the price VI is optimal. Okay, so XI, capital XI, is the set of markets where charging the price VI is optimal. Okay, and this is how market and optimal prices are related. Okay. For those of you who have seen a version of this problem with a continuum of valuation, let me just insert here a slide. Okay. The standard model that you might have seen is one where we have a continuum of valuations V. There's a probability distribution, a cumulative probability distribution, capital F of V, and a density, continuous, smooth, and so on, small f of v. Okay. If we are asking what is the optimal monopoly policy, we know by a result from Zackhauser and Riley that the best thing we can do is always to charge a single posted price. Okay, so if the consumers all have unit demand for the object, then the best thing I can do is to try to find a price which maximizes my revenue. What this means is that I want to find a price P so that the probability by which I can sell, which is simply all those people who have a valuation P or higher, which according to our model is simply 1 minus capital F of P. I want to find a price P that finds and settles this trade-off optimally. Okay. This is a simple optimization problem. I can look at the first order condition, or FOCs abbreviated. I differentiate with respect to P. And what I get is a first order condition that says, at the optimum, I must optimally balance the marginal revenue, which is by increasing my price a little bit, or by decreasing my price a little bit, I'm gaining P, F of P from the marginal, a buyer, okay, but I'm losing revenue from all those people who actually would be willing to pay more. Well, how many of them are there? Well, it's precisely 1 minus capital F of P. This trade-off between attracting a marginal buyer and losing revenue on the inframarginal buyers, I want to solve this optimally at the first order condition, okay? Therefore, what I'm looking at is to find the critical valuation V, where this first order condition is just satisfied. And so this is the last equation that I have on the slide, okay? And I simply rewritten it a little bit, namely I have taken the first order condition and divided by the density. What I get is an expression that has the value V first, and then has what is referred to as the inverse hazard ratio, namely 1 minus the cumulative probability, 1 minus f of b divided by the density. Okay. It's the inverse hazard rate. The regular hazard rate is simply the density divided by 1 minus capital F of b. And that expression is actually something which you might have heard from Peter, is often referred to, and due to Roger Myers, and that is the virtual value, okay? And it represents the value that a buyer contributes to the revenue of the producer. Therefore, it's a virtual utility. It's not the utility, but it's the utility that is relevant for the seller, and therefore virtual utility. This expression virtual was formed by Myers long before we talked about virtual worlds. And so optimal monopoly pricing is basically optimal mechanism, revenue maximizing mechanism designed for just one bidder, but the key expression, the virtual utility, appears here as well. Okay, so this is a slight aside. This is what would happen if we have a continuously differentiable probability distribution function, where we could capture the idea of optimality simply by local optimality condition necessary, and then with some monotonicity also sufficient conditions that can be captured by the first order condition. Today, we're going to use much more geometry rather than calculus as a main tool of our analysis. And so it will be useful, rather than to have a continuous and differentiable probability function, to simply have a finite probability function. And therefore, optimality is not going to be described by first order conditions, but simply by inequalities of the form that we have seen above here in the first version, in the first inequality. Okay, so we're going to basically, wherever typically you would see calculus and first order conditions, today we're going to see inequalities that represents optimality. Okay, I hope this little detour was helpful to relate a model with a continuum of valuation to the model that we're looking at today, which is a model of discrete finite valuations. Okay? The underlying consumers are still modeled as a continuum of consumers. Okay. Yes. Excellent. So we have a well-defined model, and we can therefore now start with the analysis. Okay. What we're starting out with is that we're saying we have an aggregate market. Let's call that X star. So this is the specific market that the firm is facing. The firm knows that in the aggregate, the relative proportions of valuations V1 to V capital K are given by X1 star up to X capital K star. Okay. And for this aggregate market, I can now think about what is the optimal price. Okay, that optimal price will end up being one of the valuations, right? it doesn't make sense to set a price anywhere between these finite valuations. So I want to land right on one of the valuations. And let me identify it by VI star. So that is the price that is optimal, and that is the marginal consumer with the marginal valuation that I just want to charge, so that I can get a higher revenue than I could through any other possible pricing policy that I pursue. Okay, so P star is the optimal uniform monopoly price, and it will give me a revenue, which is simply, I'm trying again my pencil here, but it seems to have stopped working, so I will have to fix in the break what is the issue, which simply gives me, okay, the revenue which is on the left hand side. And good. So now let me try to give you, I said we're going to use a lot of geometry today. Let me try to give you a visual representation of what the aggregate market is. Okay, and the example that I'm going to use all throughout today is a market that has a uniform distribution over 3 values, 1, 2, and 3. Okay, I can depicture this in this probability simplex, in this triangle, where the vertices x1, x2, and x3 are simply the mass points where only valuation 1, only valuation 2, or only valuation 3 are present. Any point in the interior of these vertices is going to give me a market where I find valuations, where I find all 3 valuations. Okay, the barycentric point, the center of the probability simplex is at 1/3, 1/3, 1/3, 1/3. Okay, and that's the market that we're going to look at. So the aggregate market looks like it's uniformly distributed between 1, 2, and 3. That's our leading example today, but the analysis will be general. Okay. Okay. Good. Okay, so X star, the point in the middle, is where we are. Okay, and we can then ask, what are the optimal prices, or what would be the optimal prices to charge? And so this gives us the division, or if you wish, the partition of this probability simplex into these segments that I introduced earlier, namely capital X1, capital X2, and capital X3, where it is optimal to charge the price 1, 2, or 3 respectively. Okay. And so if our aggregate market is a uniform distribution, what we see here is that optimally I would charge the price 2. Okay. And it will be easy for you to convince yourself of that, because if I were to charge a lower price, say 1, then I would sell to all of the consumers. So I would sell with probability 1, but I would only get a revenue of 1. So that gives me an expected revenue of 1. If I charge a price 2, then I'm going to get a sale with probability to 2/3, namely to people who have value 2 or 3. And therefore the expected revenue is 4/3, which is larger than 1. Okay. Or by contrast, if I'm charging price 3, then I will get only probability of 1/3 of making a sale. And so my expected revenue is back again down to 1. So clearly setting a price 2 is optimal. Okay. If you look at these market segments, capital X1, capital X2, and capital X3, and they basically are a partition of the probability simplex, except that they share common boundaries. Okay, and at these boundaries, we find therefore an expression of indifference, namely, if the market, our small market X, were to be on one of the boundaries, then it would simply be an expression of the fact that the revenue that I would get from choosing either one of the 2 policies or either one of the 3 policies would be the same. So I would be indifferent as a seller to choose exactly which price to choose. Okay. Okay. So we have now a way of looking at the aggregate market. Now let's think about how do we think about segmenting the market into many small segments? Okay. A segmentation is simply a probability distribution over the set of markets. Okay. A priori, in every particular segment, think about New York City, think about Philadelphia, think about Miami, think about New Haven. Every one of these segments, so the aggregate market, let's think about, is the US. I can think about segmenting it in all to the major urban centers and then the rural countries. So that would give me a probability distribution, sigma. And sigma x would simply say, well, what's the proportion of the population in the segment that has a particular composition x, right? So a richer city, say New York City, will have people which have a higher willingness to pay on average. A poorer county, say in Pennsylvania or Ohio, will have a typically lower willingness to pay. Okay. What segmentations are possible? Well, we can essentially choose any segmentation of the aggregate market as long as we are distributing the population over these markets, so that when we sum up, we're going to get back our aggregate market, right? So we can basically split up, say geographically, the US in many, many different regions, in states and counties, or in any other ways, so that in the aggregate, we are basically getting back the US. If we really could split up in any arbitrary way, then this equality here that says the sum over the segmentation give us back our original distribution is really the only restriction that we face. Okay. Right. And if we had all of these different small little segments, and if we had the ability to basically localize pricing, then we would have a strategy which tells us for every segment, we would charge possibly different price. We would charge a different price for the service in New York, then in Philadelphia, then in Miami, and so on. Okay. Right. So this idea of segmenting the market, subject to the constraint that the sum over the segments needs to be the aggregate, is quite natural. But let's see how this works out in the example that we're doing today, just to be sure that we are understanding what we're happening. Okay. So we started out with the uniform market with 3 values. Let me suggest to you a segmentation into 3 submarkets. So market 1, market 2, market 3. Okay. And in that market, we are changing the relative proportion relative to the uniform price. Okay. And so in market 1, if you follow through, I'm very befuddled why this started working. The pencil is fully charged, so but it doesn't respond. So I will have to check. In market 1, the composition now shifted away from the middle point and gave more to the low valuation and less in market 2. It's a market that has more of the high valuation bidder, and market 3 has only the middle valuation bidder. Okay. Now, each market, as I described it here, forms a probability distribution, right? So if you sum up the rows, if you sum up every row separately, it sums up to 1. So it's a well-defined market. But of course, different markets, different sub-markets may have different size. So I'm going to say, I'm going to give them different weight. The first market, I give away 2/3. Second market and third market, I give weight 1/6. Okay. If I multiply the weights through with the probability distributions, then what I find is a joint distribution over market segmentation and valuation of the following form. Okay. So now you should verify that if I sum up the probabilities in the entire matrix, I come to a probability of 1. And if I sum down the columns, then I come to the result that each value has equal probability 1/3. Okay. So what this shows us is that essentially the market segmentation that we suggested is a feasible one. And in the sum, they're going to lead us back to the aggregate market. So it's a feasible joint distribution. It's a feasible segmentation of the market. Okay. And I formulated this problem directly in terms of a segmentation. Okay. And I started the talk by saying, what's the impact that information can have on price discrimination? So you rightly could ask me, well, how is it that we can attain that segmentation through some signal, some additional information that we could give the seller? Okay. And for every segmentation, I can indeed find an information structure or a likelihood function that provides enough information that the conditional distribution of values is in fact equal to the segmentation that I claimed it to have. Okay, so let's see how this works for the uniform example. So I'm going to say, as a function of the true value of the consumer, I'm going to send out the signal to the firm, and the firm is then going to update, okay, on the basis of the signal. And on the basis of the signal, I therefore have a conditional probability distribution over the valuation of the consumers. And I'm going to take that as to be the segmentation that is induced by signal 1, signal 2, and signal 3. Okay. So let's read this off. Let's read this matrix off by going down the columns. So let's say I'm having the consumer has a value V1. What are the possible signals that the firm could see? Well, actually, there are 0 entries and just 1 positive entry. So whenever the value is 1, then we are only generating signal 1 with probability 1. The picture is different when the value is 2. Then the information structure is going to send either one of the 3 signals, and either one of the 3 signals is going to be sent with different probabilities that I specified for you. Likewise, when the value is 3, I'm not going to send signal 3 ever, but I'm going to send signal 1 and signal 2. Okay. So clearly this signal contains information. Okay. I will never, as a seller, observe signal 2 or signal 3 and believe that the value of the buyer is low, is 1. Okay. So the 0 entries basically mean that I'm going to have 0 support on those values. Okay. And if we focus just on the support, that is where the probabilities are equal, positive, and different from 0, what we see is that signal 1 leads to a conditional distribution that has full support on the values. Signal 2 has support on 2 out of the 3 values, namely V2 and V3. And signal 3 leads to a support only on a value 2. Okay, so different signals supporting different supports on the values. That's going to be a key point in the construction that we're going to pursue. Okay, right? So okay, so what's this final matrix that I'm going to present you? It's basically thinking about what is the segmentation in every one of these markets. And the rows are now identified by the support of valuations in that market. So by support, I simply mean those elements that have positive probability. Okay. If the set is 1, 2, 3, then what we're saying is that values 1, 2, 3 have positive probability. If the set is 2 and 3, then what we're claiming is that only values 2 and 3 have positive probability. And if the set is 2, then only value 2 is in the support. And that's precisely what this matrix, what happens in this matrix. These are just examples of probability distributions with changing support. If you now go carefully through, and I invite you to do the math, you will find that whenever the support is 1, 2, 3, in fact, the price is 2 is optimal in these markets, but something more is true. 1 is optimal also, 3 is optimal also. So the seller is actually indifferent to charge any price in the support of the segmentation. Okay. Another way to say that is that these segments have a distribution so that the demand has unit price elasticity, where really elasticity here is our standard notion of demand elasticity, meaning that the seller is indifferent between charging any price that is in the support of the distribution. And these segments, these special segmentations, in fact, is what we're going to call extremal markets. And they're extremal in the sense of this indifference. And they're going to be extremal also in the geometric sense that we're going to illustrate next. Okay. Okay. Good. So we are back at our picture of or the probability simplex or the market simplex. Okay. And what I plotted for you here are the 3 extremal markets that just came up in this example: x1, 2, 3, x2, 3, and x2. These are the points that are boundary points for capital X2, okay? And boundary points where, in fact, the seller is indifferent between charging at least, is indifferent between charging any prices that are in the support. Okay. What's more, and that's indicated here by the dashed lines, is that what the example suggested is the segmentation of the original market X star into a convex combination of x1, 2, 3, x2, 3, and x2 that in the sum satisfies our summing up constraint or the aggregation constraint. So what we did in this example is to basically split the aggregate market into 3 extremal markets. Okay. And because they're extremal markets, something interesting is true. Okay. And I'm going to refer to that as minimal pricing. Namely, there exists in all of these segments an optimal policy, okay, that always charges the lowest price in the support of the segment. So in the segment 1, 2, 3, I'm going to charge the price 1. In the segment 2, 3, I'm going to charge the price 2. And in the segment 2, I'm going to charge the price 2. Okay. If I'm charging the lowest price in the support of every segment, then what happens is that all the consumers who are in that segment will actually be willing to buy. And therefore, we're going to get an efficient outcome. Okay. And that efficient outcome is going to be one that therefore maximizes the social surplus, but more importantly, it maximizes the consumer surplus. Remember, I'm indifferent between any price in the support. Okay, so therefore, there exists another optimal policy. That is, we have two optimal policies, at least two. And in that optimal policy that I'm thinking about now, referred to as maximal pricing, I'm not going to charge the lowest price in the support, but I'm going to charge the highest price in the support. Okay. So therefore, if the support is 1, 2, 3, I'm going to charge price 3. Also, if the support is 2 and 3, I'm going to charge the price 3. And it's only in the case that I have a singleton, 2, that I don't have a choice, and that minimal and maximal pricing coincides, and it's 2. Okay. Now, in that pricing policy, quite a dramatic contrast arises relative to the minimal pricing. Namely, now we're selling only to one part of the consumer, only to that consumer that has the highest willingness to pay 3. And we're failing to sell. That is, we have inefficiency. We're restricting, we are rationing the demand of all the buyers who have a willingness to pay 1 or 2. And therefore, we're getting at a very inefficient allocation, both socially and, of course, from the point of the consumer. He now only buys when he's just barely indifferent between buying and not buying. So the consumer surplus is, in fact, 0. Okay? Right? So this is, in a nutshell, and an example, the entire representation of the triangle that I gave you before. Okay, the surplus triangle that I gave you before had 3 vertices. The first vertex was the top vertex that gave me perfect price discrimination. And then I had 2 vertices at the bottom where the profit was actually equal to the uniform price profit, but consumer surplus was either 0 or was at the boundary of the socially efficient surplus. Okay. The minimal pricing supports precisely that vertex where consumer surplus is maximized. The maximal pricing supports precisely the minimal consumer surplus, the most inefficient outcome. Okay. So basically, at least for this example, we have now described how we can attain the 3 vertices of the surplus triangle. Right? We're talking about information here. We're talking about complete information on the top and partial information at these 2 bottoms points, 2 lower vertices. Okay. How can we realize any point in the interior of the surplus triangle? Well, we basically can randomize. That is, we can choose to either send out perfect information or to give out information in the form of these 2 information structures. That again is a information structure, valid information structure. So what you can see now is that once we have identified the 3 extremal points in the social surplus triangle, we really have identified the entire surplus triangle. And so our work has been done. Okay. I gave you the idea of how we can do that by means of this particular example. And so in the last 15 minutes, we can now work a little bit through of how we can make this argument general and not have it just work for 3 valuation, 1, 2, 3, and the uniform distribution, but for any finite number of valuation and for any arbitrary distribution in the aggregate market. Okay. Yes. Excellent. Good. So let us now define a little bit more precisely what we mean in a general setting by extremal markets and how we're going to use that to come to our result. Okay. Good. So we already saw by means of the example that what is key for the construction is to think about the support set. Okay, that is, the set of valuations that have positive probability in a particular segment. Let's that support set be called S for a generic support set, and it contain any valuation V1 up to Vk. It doesn't need to contain all of them, but it needs to contain some of them. And of course, it's different from the empty set. Okay. For any support set now, capital S, we're going to define a particular market, X superscript S, as the market which has the features that no consumers has valuations outside the set S. Okay. So all probabilities outside of S are 0. And the second key property, that the monopolist is in fact indifferent between every price that is in the support set. Okay, that is every VI that is in the support of S. Okay, that is basically the definition of a unit elastic demand, because since a monopolist is indifferent, it means that the expected value is simply, the expected revenue is simply constant. How can that be? Well, a lower price gives me a lower per unit sale revenue. But if I'm making more sales, then it might well be that the lower price is offset by a higher volume. Okay. Here we're simply saying that the volume is happening to be exactly offsetting the decrease in the price. Okay. And in fact, okay, give me a support S. If I'm now asking what is the vector XS, okay, then that vector XS is uniquely defined by a set of probabilities, okay, and in fact that probability is nothing else. That probability vector is nothing else than a discrete version of the Pareto distribution. Okay, that's a well-known distribution in statistics. Okay, because I'm insisting that the revenue is constant for all prices, it means that the probabilities have to adjust in an exact way. And since I'm saying it's indifferent across all the support, that basically uniquely determines the probability vector or the probability entry xk capital S. Okay, and so for any S, we know this is uniquely defined, and XS is referred to the extremal market. Okay. Right. So, what are the extremal markets that involve the valuation 2? Those are depicted here. Right. So I'm just giving you a zoomed-in version of the probability simplex that pictures all those extremal markets that includes 2. Of course, it could mean that in the market is just the valuation 2 that's present. That's the lower right vertex. It could mean that it's just a market in which only 1 and 2 are present. That's the lower left vertex, x1, 2. Or the top right vertex, the top vertex, x2, 3, has the market where only 2 and 3 are present. Or finally, it's a market where x1, 2, 3, where in fact the seller is indifferent between charging any one of the 3 valuations. Okay, so here you have the geometry of extremal markets as the vertices, okay, that form the convex hull of all the market segments in which 2 is an optimal price. Okay, right? So all of the points in the interior. Okay. Formally, we want to think about the set of markets xi star as those markets where it's optimal to charge the monopoly price vi star. Okay, so that simply gives us a collection of all possible markets where it's optimal to charge vi star. Okay. And S star is a subset of subsets that contain I star, right? So we have a support, that's S. If I star is included in the support, then that gives us a set, that gives us a support, and all those sets that have I star in the support are identified by script S star. Okay. Okay. And the result that is really an application of a famous result from convex analysis, the Minkowski-Carathéodory example, theorem, sorry, is that xi star, that is the markets where it's optimal to charge the price vi star, is exactly given by the convex hull, that is by the hull that is spun by the extreme markets where I is included. Okay, so this is just saying that the picture that I gave you here, which depicts all of the markets in the interior of the vertices that I show you, that includes 2, is in fact spanning the set of all those markets where it's optimal to sell to. Okay? And this is the unique representation, if you wish, in terms of these extreme points of when it is optimal to set a price I star. Okay. Okay. The proof is here. It's really a simple proof by contradiction. So let me skip that, but raise it to your attention and ask you to read it. Okay. Okay. And so what we did in the example with 3 values, we can now do more generally. And we're going to simply take any aggregate market, split it into extremal segmentation by the lemma that I gave you. I know that I can do that. Okay. And the resulting segmentation allows me then to introduce 2 pricing rules, namely the minimum pricing and the maximum pricing, that gives me any point on the bottom of the triangle. Okay. So this is the minimum pricing rule. Okay. So let me just switch forward here. This is not so useful to do in steps. Okay. Since we saw them already. So we have a minimum pricing rule that implies efficiency. I'm basically setting a price for every segment that is at the lowest point in the support. That gives me efficiency and consumer surplus maximization. A maximum pricing rule gives me 0 consumer surplus, okay, and a very inefficient allocation because many consumers are priced out of the market. And finally, any pricing rule that just uses the support of the extremal segments will give me also an optimal rule, and it will keep the monopolist at his uniform monopoly profit because it always includes our original price and our original valuation. Okay. Right. So that is the result. That is, we can attain an extremal segmentation. I showed you how to do it. The producer surplus is under those state constant, but they led to very different distribution across the consumer surplus. With maximum pricing, I got 0 consumer surplus. With minimum pricing, I basically make the consumers the residual claimant of the social surplus after conceding to the seller the uniform monopoly profit, but not more than that. Okay, good. This is the main result, and this is the first main result, and I'm going to restrict attention to this main result. Okay, why? I want you to think about the result now slightly different. Namely, I want you to think about this result as telling us something about how impactful and how important information can be. That is, the segmentations that we created, namely the segmentation that led to a uniform price elasticity, okay, to unit price elasticity, had the implication that it allowed for at least two different pricing strategies. One where consumer surplus is zero, one where consumer surplus is in fact very high. So what this suggests is that information is very powerful to guide the incentives or to provide incentives and therefore to guide actions for, in our context, the seller and then, of course, the buyer making purchases that have a substantial influence on the nature of the social surplus that we can realize. Okay. So far in this class, we saw how we can provide incentives through allocation probabilities or assignments, what do we give the winning bidder, and through determination of the transfers, that is the monetary part of the incentives. Okay, so we provided incentives essentially through allocations, in particular through monetary allocations, that allows us to elicit the right demand or supply information, or the true demand and supply information from the buyers. Okay. In this class and in this analysis of price discrimination and segmentation, we saw something else. We saw that information, the provision of information, can noticeably affect the incentives and the actions undertaken by the participants in the market, and then can therefore have a substantial influence on the realized social surplus. Okay. And therefore, the question of how to provide information optimally, how to design information optimally to achieve a social objective or a private objective, is a seemingly important subject. And as we saw here in the analysis of price discrimination, one that had quite a big impact. Okay. So this is what we are then going to look at in the second class today. Okay. And I want to just provide for a minute additional motivation of why the design of the segmentation, the provision of the information structures might be particularly interesting and suggestive of what happens in real markets. Okay. This is, of course, it was a theoretical and analytical exercise that we did here, and we pushed in some sense the boundary of what we can achieve with information to the extremes. That's why we call them extremal segmentation. But think about the impact that you could have by choosing segments endogenously. Okay. The notion that I want to suggest to you is that in much of the digital economy today, these segmentations are not going to be given exogenously, but rather might be chosen endogenously. So when information is provided to advertisers on sponsored search, then Google, knows pretty much everything about consumers and advertisers. Is probably not a statement that's too far as an approximation. And then the question is, what kind of information does a platform want to provide to the advertisers, to the bidders, or to the consumers about the value of the product, so as to maximize social surplus, which maybe the objective of the platform, because the platform wants to attract as many buyers and sellers to its site. Okay, so the provision of information, the optimal provision of information, is probably a big part of what the optimal design of a digital platform is, and therefore it makes sense to think a little bit more in detail about how we provide information optimally, and that's what we're going to do in the next lecture when we talk about Bayesian persuasion. Good. So we have the second class of this Monday now. We started talking about price discrimination in the first class. We saw that information and the provision of information has substantial impact and implications for price discrimination, and therefore could influence the incentives of the agents in the market. And so today, in the second lecture, we want to think about this a little bit more systematically and in a very simple, stylized setting. Between just one agent, the principal, and an agent, the agent, or as it has been common in this literature on the economics of communication, to think about one agent as being the sender. That's the agent who provides the information, and the other agent being the receiver. That's the agent who receives that information and then has to make a choice. Okay. This literature, the economics of communication, the strategic use of information in communication, has had a long and interesting history. An important first paper was a paper by Crawford and Sobel on strategic information transmission, and has received a major boost through a recent paper, I think maybe 2012, entitled Bayesian Persuasion by Emir Kamenetzer and Matt Ganskow. And so today the talk will be based on some slides that Emir was kind enough to share with me. And so thank you to Emir. And where we're going to basically think about the notion of persuasion, that is trying to align incentives, or trying to persuade somebody to pursue an action within the context of doing so credible, namely doing so within Bayesian statistics, and in particular Bayes' law, and hence the title that is starting this literature, Bayesian persuasion. Okay. So if we start from a very basic point of view and asking ourselves, well, suppose I wish to influence somebody's action, then essentially that within our economic models can happen through two channels. We can either change the payoffs. Okay, that's what we saw in the earlier lectures in mechanism design, or we can change the beliefs of the agent, and that's what we saw indicated today in price discrimination. I'm going to see now in much more pure and therefore sharper form. Okay. Whoops, I didn't do. Okay. Now, attempts at persuasion command substantial resources, right? So you can just ask yourselves, where is, I'm moving too fast here, where is persuasion used? And much of marketing is basically an attempt to provide, or think about advertising as basically providing information to steer a recommendation. But of course, many other forms of policies, information policies, are meant to steer actions, to influence some actions. Okay. Now, as I mentioned, there's a long literature on strategic forms of communication, and those in one way or the other, may seem to suggest at first glance that persuasion is impossible. Okay. Why do I say that? Well, if you think about cheap talk games, so these are games where the sender is sending a message, but one that has no cost to him and has no verifiability either, then in cheap talk games, really the sender can say anything he wants. The receiver will know that the sender is basically just trying to influence him and will therefore disregard the messages, so no communication happens. On the other hand, there are games that are often referred to as verifiable message games, where I can only send messages that correspond to the truth, but not the whole truth. So, for example, I can communicate elements in a partition, but of course the true state must be in the partition. Then there are many models that basically show that communication is unraveling. So the sender will eventually perfectly reveal the state. So in that sense, persuasion is also not possible because it always leads to complete and full communication, but not anything in between. Okay. So let me state these two impossibility results formally with a model, and that's going to be the model that we then later are using also for the Bayesian persuasion setting. So it's helpful to do it right now. So we want to think about the seller, the receiver as the one who will eventually choose an action A. And his utility function depends both on the action that he chooses and the true state of the world. The problem for the receiver is that he does not know the true state of the world. We'll keep our life simple and are going to think about the sender as one who always wants to see the highest possible action, and the sender knowing the state of the world. Okay, so this is a statement both about the preferences as well as about the information. In this setting, okay, the receiver is anticipating already that the sender would like him to choose not the action that is most suitable for the state, okay, but choose unconditional on the state the highest possible action. Okay. Well, cheap talk means that the sender can send any messages regardless of the truth. So it's cheap for the sender. And the equilibrium analysis is so straightforward that we don't have to do much formal analysis. The receiver anticipating the intent of the sender and knowing that he can always send any message, will therefore always do best to simply ignore the sender's message and choose an action that is based just on the prior distribution of the state. Okay. If we have verifiable message on the contrast, so the sender cannot tell explicit lies, then in the setting, the result is called the equilibrium result. The equilibrium analysis will tell us that the entire truth will always be revealed. Why? Because we know that the sender would like the highest possible action. So if the state that he's informed about is one that would lead the receiver to choose the highest possible action, then he would reveal that. If it's not, well, then he has already revealed that's not the highest possible state. And it might be just the second highest possible state. But now by induction, we can infer that the sender again would have an incentive if he's restricted to just report anything between the lowest and the second highest possible state, then again he would like to report the second highest possible state. So this process unravels, unfolds, and in equilibrium, the sender will find it optimal to always reveal the entire truth, because absent of that, the receiver will make the rational inference that the state is the lowest possible state. Okay. So I would maybe not refer to this as the impossibility result as Emir does here, but either way, there's little scope for persuasion in the sense that the eventual equilibrium outcome is determined independent of the prior distribution, and it's just a function of the state of the world, and in fact has an extremal outcome in the sense that under cheap talk no information is revealed, whereas under verifiable messages all of the information is revealed. There's no solution in between, that is, we don't get partial, additional, augmented information. We either get zero information in one class of games, we get full information in another class of games. Okay. How are we going to make life more interesting and richer? Well, we're going to assume that, or we're going to think about the setting where the sender can in fact commit to an information policy. Okay, that is, can commit to an information policy, a messaging that basically allows him to adopt a policy that says, as a function of the true state, here is a signal that I will send you, or here is a probability distribution over signals that I will send you. And what we will see is that with this ability to commit, a richer set of possible messages arise, and a richer set of possible information and policy arise that can be chosen optimally in equilibrium, and that will often give us result that there will be some information transmission, but there will be more than zero information transmission, but less than complete information transmission. So typically we will be somewhere in between. Okay. These are big words and big plans. So let's start with a simple example that should make you familiar with the sender-receiver environment that we're setting in, and also about the role that information can play within it. Okay. So the example is one from law and economics. We think about a trial where there is a defendant that can be either innocent or guilty. So the state 0 is representing his innocence, the state 1 is representing his guilt. There's shared prior, which is simply saying that the likelihood that any arbitrary defendant is guilty is 0.3. We have two players. It's a judge who is the receiver, who will have to make a decision conditional on getting information from the sender, whom we refer to as a district attorney. So that's the prosecutor. Okay. The judge is impartial. That is, he wants to make the right decision given the true state of the world. That is, he wants to acquit or choose action 0 if the defendant is innocent, and he wants to convict if the defendant is guilty. Okay. So in other words, he wants to match the action with the state. And whenever he manages to do that, his true payoff is 1. If he fails to do that, if he acquits but the defendant is guilty, then the payoff is 0. Or if the defendant is guilty but he acquits, okay, or if the defendant is innocent but he convicts. Okay. The district attorney, on the other hand, is building a career, a reputation of convicting as many as possible defendants. So he gets a utility of 1 if indeed there's conviction, and a utility of 0 if there's a acquittal. Okay, so the sender strategic possibilities are just to influence the receiver's information. The receiver will process the information and then will take an appropriate action decision. Okay, so it's basically a two-step game. In the first step, the information flows. In the second step, the information is processed and then leads to an optimal action. Okay. Notice that the utility function of the sender and the utility function of the receiver are quite distinct. So a priori, their preferences are not at all aligned. Okay, they agree in the state of guilt, but they diverge in the state of innocence. And the question is, how, for the district attorney who's the sender, how can he use the information to move the judge in a direction that's favorable in terms of the utilities of the district attorney? Okay. So the instrument that the sender has is really just the structure of the information. The instrument that the judge has is the appropriate decision that will have payoff implication, not just for him as a judge, but also for the district attorney. Yes? Okay. So DA is English for district attorney. He will provide information. We want to think about the information as basically an investigation that he conducts, and the outcome of that investigation, it may be random, will then lead to information that the judge will use to come to a judgment. He can choose subpoenas, he can choose forensic tests, he can choose to question the witnesses. So there's a whole bunch of investigation, literally tests, that the district attorney could run in order to get more information. Okay. The outcome of the investigation is observed by the judge. So we think about the outcome of the investigation as the signal. Okay, and so there's commitment to an information policy because the district attorney basically communicates to the judge that he's going to use a forensic test or that he's going to question the witness, and the outcome of that test will then be observed. Okay. Let's be sure that we understand the implication of these investigations for our decision problem, right? We said, perhaps it might be useful to just go back by 1 second to the initial setting. We said that the judge is going to make a decision based on the information that he has, and then is then going to try to maximize his expected utility. The utility is matching state with action, okay? And so in the absence of any information, any additional information, or any investigation whatsoever, the prior is sufficiently favorable to the defendant that he's going to be acquitted, right? The probability that he's guilty is below 1/2. Therefore, in the absence of any information, it's optimal for the judge to acquit the defendant. Okay. If, on the other hand, the investigations are flawless, that is, are going to reveal all of the information for sure, then what we know is that with probability exactly 30%, the defendant is going to be declared guilty, right? That's simply the distribution by which he's guilty. And with 70%, he's going to be declared innocent. So the outcomes are quite different, okay? With no information, he's always going to be declared innocent. With complete investigation, there's a 30% chance that he's declared guilty. Okay. Right. And that's what we summarize in here. But of course, investigations can be leading to different informational contents than the one that we are talking about in the moment. And in particular, it could lead to outcomes that are neither given by zero information nor by complete information as under these two extremal investigations. Okay. right? And in particular, if you put yourself into the position of a district attorney, then you might ask yourself, well, is there an investigation that I can pursue where the probability of getting a conviction is higher than 30%? So here is a partially informative test that is information theoretic. So if you think about the amount of information that's provided, somewhere between 0 and complete information, but it will have interesting implications for the decision of the judge. Okay, so among the things that were found at the crime scene, we found the blood of the murderer. We don't know who the murderer is, but we found his blood, and it's type A, and it's found at the crime scene. Okay. Therefore, what the district attorney does is he requests the tests of the defendant's blood type. Okay. Okay. The possible outcomes that are being generated by this test are quite simple to describe. Okay. The test is perfect in terms of identifying the blood type. Okay. If the defendant is not type A, okay, then clearly he cannot be the murderer. Okay, because the murderer's blood type is A. Okay. If the defendant is of type A, then of course it increases the prior probability, and we can compute what the posterior probability is that that person was indeed the guilty defendant. Okay, so we have observed that the blood type is A, therefore we can compute by Bayes' law, by Bayes updating, what the probability of the defendant is of him being guilty, right? And so this is just standard Bayes laws, and we do the calculation with the probabilities as we have been given them. Okay, then we find, okay, that the probability of guilt of the defendant after it was found that he indeed shared the blood type with the murderer has increased. That's what we would expect, and has increased to a little bit over 50%. Okay, right? Okay. So now, and what are the outcomes? Well, if the judge believes that information, then the probability of guilt is 0 if the defendant is not type A, and so the judge acquits. But on the other hand, if the defendant has type A, then the posterior probability now exceeds 50%, and the rational thing for the judge is to obtain a conviction. Okay. Now you can ask yourself, how often does the judge convict? Okay, in this case, and well, if that is easy again to compute by the probability. Okay, but notice here that if the defendant is guilty, which is the first event, which is happening with probability 3, then of course he has a blood type A, and therefore the probability is 1. But even if he's innocent, he can have the blood type, and the empirical distribution of blood types in the population is simply 0.42. So that's what we know for medicine. And we just saw that the defendant is convicted whenever he in fact is found to have blood type A. So miraculously, apparently, we are now have arrived at the conclusion that we are going to be able to convict the defendant, not with probability 0.3, which is our prior probability that it's guilty, but with almost twice the probability, namely with probability 0.6. Okay, so that's quite good, at least from the point of view of the district attorney, whose sole goal is to get as many convictions as possible. Okay, because he has managed to come up with a partially informative test that is unbiased, that's just using Bayes' law, and yet that convinces the judge to convict with a likelihood that is twice as high as the prior likelihood of the defendant being guilty. Yeah. That naturally leads us to the question, could the district attorney find an even better test? What's the optimal test? What's the optimal information policy that the district attorney might adopt? And that's what we're going to try to trace out now in the remaining half hour. Okay? Any questions or issues that you want to raise? Good. Right, so that's just a summary of what we just learned. Okay. This was just one particular test. He could choose and have other tests, DNA test, rhesus factor test, and so on. All of these would have generated additional information, would have influenced the judges in a different way, and we want to ask, from the point of view of the district attorney now, what's the best, the most impactful way of providing information that aligns the actions of the receiver with the interests of the sender. Okay, so that's the objective. Can the district attorney do even better than the 60% conviction rate, which you might say is already pretty good, given that it basically doubles the true empirical frequency of guilties? Okay. Good. Good. So now we basically want to think about formally what an information policy is, what an information structure is. Okay, and it really is just a likelihood function. That is, the data we already have is the prior distribution over the state omega. And an informational policy is now a specification of a likelihood function pi that tells us how likely we are to send a signal, okay, given the state. Okay, so let's think about a simple binary signal, okay, that we label either G or I, small g or small I, for meaning it is meant to convey information that's sufficient to have the defendant look guilty, or it is meant to convey enough information to make the defendant look innocent. Okay. Complete information is a perfectly valid information structure. Okay. And in fact, okay. And in fact, it seems that, okay, good, here we are. Right. Okay. And that would simply mean that when the state is innocent, we send the guilty signal with probability 0. When the defendant is guilty, we send the guilty signal with probability 1. The blood type the blood test that we just specified gave us the other test, which says if he's guilty, we're sending the guilty signal for sure, but we're sending the guilty signal also if the defendant is innocent. Well, we don't do it quite as often as we do it when he's guilty, but we do it sufficiently often so that we increase the conviction rate. Okay. Good. And now we want to ask ourselves, how can we get to the optimal information policy, and how can we analyze the optimal information policy? Today is the day of geometry, and we're going to do this again just by geometry, so essentially by means of a few illustrations, but the math behind this is pretty simply to implement and to realize. Okay, so here we go. We're going to have and illustrate everything in a two-dimensional diagram. And in this two-dimensional diagram, U or mu is the probability that the state is guilt, okay? And that's the x-axis. And the y-axis is going to be the action, okay? So either 0 or 1, okay? And conveniently, it is also the probability that the action is equal to 1. So I really need to check what's happening here. This is rather hard, or maybe this is hard because it is so, no, anyway. Okay, good. Okay, so here's the situation. We know what the optimal decision is of the receiver given his posterior belief mu, okay? Namely, if his posterior belief mu is somewhere between 0 and 1/2, then he thinks it's more likely that the defendant is innocent, and he is therefore going to acquit. That's action 0. On the other hand, if we move to 1/2 or above, at 1/2 we're indifferent, so we might as well convict. If we move to 1/2 or above in terms of the posterior probability mu, then we're going to convict, and we're going to get to an action that is 1. Okay, good. We can also think about this now, not as just defining the action, but also defining the utility of the sender as a function of the posterior belief of the receiver. Okay, so let me just erase, therefore, this first picture. Okay, and again, I'm stuck here and I really don't know what's happening, so I'll need to work on this a little bit harder next time. And in fact, I'm wondering, no, I'm good, stick with this. Okay, good. Good. So we have a two-dimensional diagram. On the x-axis is the posterior belief of the receiver. On the y-axis is the action of the receiver, but the action of the receiver is also the indirect utility of the sender given the belief of the receiver. Yes? Okay. So very much the sender would like the receiver to have a posterior belief that exceeds 1/2, because then he's going to be able to get the receiver to choose that action and will realize a utility of 1. Okay. An outcome of the investigation induces a belief mu. Okay. That's how we thought about the investigation. That's how we think about the information structure. An investigation induces a distribution of beliefs, right? We are committing ourselves to doing a blood test, but what the outcome of the blood test is then a function of both the quality of the test and the underlying condition of the defendant. That is whether he has blood type A or not. Okay. Okay. So again, let us go through the example. Okay. If we do no investigation, then the posterior belief is going to be the degenerate one that is going to stick at the prior belief. Okay. If we have a fully informative test, then we're going to split the beliefs from the initial point 3 to the posterior belief 0 and 1. Okay, and we're going to do that with precisely the probabilities 0.7 and 0.3. Okay. This specific blood test that I suggested you that we look at had the property that it generated beliefs, okay, that were either beliefs on 0 or on 0.5. Okay, that is either the defendant was innocent or he was sufficiently guilty, right? If he had a blood type that is different from A, then he was innocent. So that's a probability, the posterior belief mu equal to 0. But if his blood type was A, then that led us to a posterior belief of 1/2. Okay. The only restrictions that any informational policy has to respect is that the expected belief over all the signal realization equals a prior, right? And that's simply the total law of probability, that's space consistency, okay? The information that we get will refine our beliefs in terms of the posterior likelihood, but it will be linked together by the law of total probability, namely, on average, it must be that 0.3 times it is he's guilty, 0.7 times he's innocent. Okay. So this aggregate constraint that the expected beliefs have to equal to the prior is very similar, or in fact is just another instance of this aggregate constraint that we saw earlier on when we spoke about the segmentation of the markets, where we said that the segmented markets have in the sum to aggregate up to the market distribution, and that's exactly the case here as well. Okay. Okay. And we can say this formally also in a sense that we want to be sure that when we choose the optimal information policy, the set of feasible information policy is indeed this large, okay? And indeed one can show that any distribution of beliefs, as long as expectation is the prior, there is an investigation that induces it, okay? So really, our feasible choice set of information policies is as large as indicated in the proposition, and in fact, exactly coincides with those. Okay. So here we go again, right? I'm simply now going to illustrate to you what these investigations that we spoke about by example do in this two-dimensional diagram. And then I'm going to suggest to you that, in fact, the optimal investigation, the optimal test, the optimal information policy follows by pursuing the logic of this diagram to its very end. Okay, good. So if we chose to not have an investigation, then we are going to land at our prior, which is the red dot, and we're going to get 0 conviction rate. That's not a great outcome for the district attorney. Okay. If we have a fully informative investigation, okay, then we either end up at posterior belief 0 or at posterior beliefs 1. Okay. If we end up on posterior belief 0, then we're going to acquit the defendant. If we're going to end up with posterior belief 1, then we're going to convict the defendant. Okay. Now, okay, what is the utility? What's the expected probability by which we're going to convict the defendant? Well, it's simply 30%, okay? And it's simply the convex combination, okay, between these two extreme points, okay, that is equal to the prior, which is the red dot in the middle. Okay. Yeah. So you see that this perfectly informative test can be modeled here, and it's what you just see on the graph. Okay. Okay. How about other tests that we could run? Okay. Well, I could run less than perfectly informative tests. So, for example, I could run the test that is identified by the 2 dots that are on the lower and the upper black line. Okay, these are posterior beliefs that are neither 0 or 1. Okay, but there are one on the lower line and one on the upper black line. And so whenever that posterior belief obtains, we know that either acquittal or conviction obtains. Okay. If for some reasons we were choosing a test that generates those precise two posterior points, the one on the lower black line and the one on the upper black line, then the convex combination can be computed as that convex combination between the 2 points that lands up precisely at the prior, which is the mu0. Okay, and as you can see, this generates very few convictions. Why? Because whenever we get the convictions, we are almost sure, we're very close to 1, but whenever we don't get the convictions, we are actually very much in the interior of the belief. So there's a good chance that the guy is guilty. It's just that we don't have the right evidence. And so in total, we're basically convicting very little. Okay. So now you may ask yourself, how can I place these two red points on the upper and lower line so that the convex combination of the two, okay, gives me a prior and gives me a prior that in fact pushes the probability of conviction as high as possible. Okay. Yes. Okay. And you see that's done by basically moving the 2 points to the left. Okay. And in fact, it's being accomplished by moving the 2 points to the left as much as possible while still keeping them on the upper and the lower black line. Okay. Good. Right. So let's look at this. Okay. What have we achieved? We are basically making a claim that the optimal information structure is 1. Okay. Okay. Is 1 that gives us two posterior beliefs. One at which I'm fully convinced that the defendant is innocent, therefore mu is equal to 0. In one at which I'm barely convinced that he's guilty, that is the posterior belief is 50%. Okay. If I distribute the information in such a way, I'm getting to a prior belief that makes me sending the negative signal, namely the signal that leads the judge to convict the defendant, as frequently as possible, namely close to 60%, and that's the red point in the middle. Okay. Okay. Good. That is essentially the picture here. Okay. What's the economics? And then perhaps what's the mathematics behind it? Okay. The economics is perhaps easy to understand. Okay. There are actions that the sender would like to see happen. Okay. Namely, he would like the receiver to convict the defendant. Okay. He can achieve that as long as he provides enough information to basically make the judge indifferent between acquitting and convicting. Okay. That happens at the posterior probability of 1/2. Okay. He would like that to happen. He is the sender, the district attorney. He would like that to happen as often as possible. How can that be? Well, the best way to accomplish that is to essentially force or send a signal of the innocence in all those cases, but only in those cases where the defendant is innocent, and otherwise leave the picture muddled leave the picture sufficiently muddled so that the judge concludes that the defendant is at least as likely to be guilty as innocent. Okay. So this is one particular information structure that basically concentrates all the bad news for the district attorney in one signal and makes in the other signal the defense attorney indifferent. Okay, so the role of indifference and the role of extremal signal again shows up here, just as it shows up in the price discrimination before. What else shows up here? Well, the set of information structures is, the set of signals that I could send is infinitely large. Okay. Somehow I restricted myself to just two signals, namely a signal that suggests that the defendant is innocent and a signal that suggests that the defendant is guilty. Okay. And that is just another version of the revelation principle and mechanism design that we have seen before. And it goes like that. There are really just two possible actions for the receiver to pursue here. So therefore, the information that we can give the receiver, it has at most to be binary as well, because any more information than that would be redundant in the sense that now several different signals would actually lead to the same action. So we might as well bundle all those signals into just one signal. That means when we think about signals and signal policy, we can think about a direct policy where we simply going to convey to the receiver the recommended action. And it just has to be the case that the frequency by which we recommend the action and the frequency of the underlying state have to be sufficiently aligned so for the incentive constraints to hold. Okay. So without loss of generality, again, we can look at the direct mechanism, which simply means here at a mechanism that has at most as many signals as their actions in the support of the receiver. Okay, so indifference is key, isolating information is key. These are basically extremal points, extremal information structures. Those we saw already in the price discrimination. That's economics. Now let's think about the mathematics, what we did here. Okay. Okay, so we basically have piecewise linear segments of a function, right? That you see here. These are the black points. And these piecewise linear functions that are the actions, or that represents the actions that the agents are taking, lead to different levels in the utilities of the sender. Okay. We want to get as high as possible, subject to base consistency, subject to base rule. So the idea here is that we can basically use the spreading of the beliefs from the prior to the posteriors, or another way to say that is we basically again forming a hull, but this time we're forming the concave hull of the utility function, and that's going to give us, by construction, the optimal information structure. Okay. Okay. So let's give us a notation to formalize it. So let capital V of mu be the smallest concave function everywhere above V hat of mu prime. That is everywhere above the utility that the sender would get under that posterior belief. Okay. Okay. The maximum payoff attainable through persuasion, the claim, is the evaluation of the smallest concave function precisely at the prior. Okay, and that's what we did here. Okay, we had the piecewise linear function. The concave closure of this piecewise linear function is given by capital V over mu, which is basically now the piecewise linear function that is in red. Okay. Okay. And therefore, we can now read off that the highest value that can be attained can be attained at V of mu0, which is precisely the prior. Okay, so this concave closure, okay, gives us two things. It gives us A, the way in which we should create information structures, and B, it actually gives us the value that the sender can maximally obtain in this game between him and the receiver. Okay, and that's that second part is illustrated here. Okay, good. Now we did this for the very special case of a binary state and a binary action model, where the utility of the sender was in fact state independent, and where the utility of the receiver was given by matching state with action, so either 0 and 1. But in fact, the result, namely that we can get both the construction of the information structure as well as the utility of the sender by means of the concave closure, that environment or that result, that statement, is true in now this general environment where the receiver has simply a general utility function in a finite action, finite state space. The sender has a different utility function in a finite action, finite state space. And we can compute what the value for the sender is at a particular posterior belief by simply identifying at that posterior belief the optimal action of the receiver and then evaluating the value of the sender at that optimal action and the true state. And the claim that we are making is that we're going to form the concave closure of V hat mu, and then the sender can attain through Bayesian persuasion precisely the value that is attained at that concave closure, evaluated at the prior belief. Okay. So to give you a sense of how this works in other examples, okay, and sort of to give you a fuller sense of geometry, right? So let us think about now a situation where the state space is still binary, so omega 1 and omega 2, and therefore the prior as well as the posterior belief is just a single number, mu, that we're varying along the x-axis. But the action space of the receiver is much richer, and so varies with the posterior belief in a continuous way, so that also the utility function of the sender, or maybe the utility function of the sender itself varies so continuously, is given by this curve that you see, and that is the graph on the y-axis. Okay. So again, we have a prior belief that is simply a prior probability mu0 of state 1 as opposed to 1 minus mu0 on state 0. Okay. And I can trace out what are the posterior probabilities that would give me a high utility. Okay. In our graph, not by chance, okay, our prior belief is such that it basically gives us not only a local, but also global minimum for the sender. So he wants to get out of that global minimum. How can he get out of this global minimum? How can he, in fact, move closer to the two local optima, that is the two hills of this graph? Okay. Well, as you can see, we basically can spread the prior belief, spread it and split it into points, okay, so that the convex combination of the two again is the prior belief, and that clearly gives us a higher utility. Okay. Oops. Yep. Right. We can move these points further up, as we move these points further up, we get an even higher utility for the sender, and the maximum is attained, okay, where we are connecting not necessarily the maxima, but something close to the local maxima here, and then form the concave closure. Okay, right. So we started out with an arbitrary function that depicted the expected utility of the sender as a function of the optimal action of the receiver, and we now computed both through the splitting of the beliefs and the formation of the concave closure that comes with it. We computed both the optimal information structure as well as the optimal value that the sender can receive. Okay. And here, the red curve gives you the concave hull and gives you the value of the sender. Okay. Okay, so we come almost to the end of our class. We saw in the first lecture that information can influence agents in market design settings substantially. And then in the second lecture, we sort of gave a very stylized version of the effect that information can have. That is recent work that started with Emir Kamenitsa and Matt Gansko's paper Bayesian persuasion, that since then has found lots of interesting applications to marketing, organization economics, political economy, accounting, and so on. Many of the applications started out by thinking about the single receiver, so basically decision problems. In the work that I've been doing, I was particularly interested in strategic environments. That is when we have many receivers and we want to coordinate the receivers. So that's a beautiful and rich area of studies. And as you saw today, geometry, linear algebra, and convex sets give us sort of a very nice set of tools to think about how to choose optimal information structures. And so I hope Emir's favorite application is to entertainment industries. There's actually a very nice paper here in the Journal of Political Economy, but we won't go that far today. We have plenty of entertainment, hopefully tomorrow, during the American elections. And so until tomorrow, we'll stop here and meet again.